Salut
Bonjour,
Nabil, tu vas bien?
très bien et toi?
Ouais, merci, bonne année.
Bonne année, ouais. Alors, chez vous, c'est pas de confinement? Confinement? Non, il n'y a pas de confinement en ce moment.
Aujourd'hui, il n'y a pas de confinement, il y a le couvre-feu
Ah,
qui est jusqu'à 20, enfin à partir de 20 heures à Paris, enfin dans la plupart des endroits, et 18 heures dans certains, et on s'attend à pas des bonnes nouvelles dans 2-3 jours.
quoi? À cause des fêtes?
Ouais, entre autres, les fêtes, le variant, enfin ça, oui, je pense que les fêtes n'ont
Ah
pas
oui, le
bridé.
variant, oui.
On le savait avant et il n'y a rien eu à faire, hein. De toute façon, les gens voulaient en marre, quoi.
Ouais.
Non, mais c'est vrai, je veux dire, là, en ce moment, tu vois, nous, on est bien, on a de la place, on n'a pas de problème de boulot, de trucs comme ça. Il y en a ras-le-bol. C'est, il a
Euh,
commencé chez vous?
ça va. Alors, en ce moment, en fait,
Où
depuis
tu
un
es, toi?
moment, c'est assez calme. Donc là aussi, ils ont peur
Ouais.
de l'arrivée du nouvel variant.
Où tu es,
Mais
là, physiquement?
là, depuis plusieurs semaines, même plusieurs mois, on est à une centaine de nouvelles infections par jour sur tout le pays.
Ouais. Où tu es, là, en Arabie Saoudite?
En Arabie Saoudite, oui, oui.
Ouais.
Et d'ailleurs,
Ouais, c'est.
ils ont fermé les frontières pendant les vacances. Donc, ça m'a fait annuler mon voyage. J'avais prévu de passer les vacances à Tunis.
Ouais, ah oui.
Et là, j'essaye de redemander, parce qu'il faut tout refaire, quoi, redemander un congé. J'ai tout annulé.
Ah oui, d'accord.
Ils ont réouvert, mais bon, je ne sais pas si je repars quand même.
Ah, même pour sortir, après, t'es pas sûr de pouvoir revenir. Là, c'est compliqué.
Alors, en fait, à un moment, pendant une semaine, tu pouvais faire ni dans un sens ni dans l'autre. Ensuite, au bout d'une semaine, ils ont ouvert à la sortie, mais pas à l'entrée. Et, et 15 jours après, donc ils ont annoncé que les frontières étaient réouvertes. Mais mon vol était déjà parti.
Ouais. Et vaccin ou pas vaccin chez vous?
Comment? Si,
Vous avez
si,
du vaccin?
ça va commencer, ça commence là. Ils ont pris le Pfizer aussi. Ouais.
Ouais. Bah oui, alors, bon, il n'y en aura pas. Il est compliqué, il n'y en a pas tant que ça, apparemment. Enfin, nous, la France avait beaucoup misé sur Sanofi, qui sortira plus tard. Et je suis assez inquiet sur le nombre de doses, quoi, en fait. Je ne sais pas
D'accord.
si tu as entendu parler, on commence très doucement ici. C'est même ridicule le petit nombre de gens qui ont été vaccinés.
Oui, oui, oui,
C'est lamentable.
j'écoute les infos. Je suis
C'est
française, donc
n'importe
entre
quoi.
autres, et donc j'ai vu ça aussi. Ouais.
Et mon avis, qui n'est pas du tout autorisé, c'est qu'il n'y a pas assez de doses de toute façon, donc c'est pas la peine de vacciner tout le monde maintenant, après il y aura un trou. Euh, Il y a un risque que tu vaccines, toi. Mais bon, tu fais le compte, hein, tu as 60 millions de personnes, si tu comptes même la moitié, 30 millions, pour faire ça en 6 mois, il en faut combien par mois? C'est pas très compliqué, hein. Donc à 1 million par mois, t'es pas arrivé, je veux dire.
Oui, oui, j'ai entendu ce matin, il disait qu'il pensait élargir aux pharmaciens, aux infirmiers. Jusque-là, il
Bah, il
voulait.
faut, bien sûr. Ouais, ouais. Là, ce matin, c'était toutes les personnes de plus de 75 ans. Et là, j'ai entendu tout à l'heure qu'ils allaient faire un numéro où les volontaires sans distinction pouvaient s'inscrire. Et après, je ne sais pas s'ils feront gérer ou pas, mais moi,
Hmm.
je suis pressé, hein.
Mais c'est bizarre parce que il y a tellement de spécialistes de logistique. Je veux dire, faire
Pas
des.
chez nous, non.
Ou alors ils appellent pas, quoi.
Attends. Ouais,
Pas au
attends,
ministère.
qu'est-ce que j'ai fait? Oui, ouais, c'est ça. Non, mais bon, c'est vrai que le Pfizer, il est compliqué parce qu'il y a la question du froid, quoi.
Ouais.
Ils ont dit qu'il faut faire comme en Allemagne, il faut faire des. Parce que là, pour l'instant, ils amènent le vaccin aux gens. Dans les EHPAD, ils sont un peu obligés. Dans les trucs pour personnes âgées,
Hmm.
ils sont obligés, il faut les déplacer. Après, il faut faire des endroits où les gens viennent. Sinon, c'est ingérable.
Hmm.
Parce qu'il faut ces frigos à moins 80, là, qui sont des trucs qu'on ne trouve pas facilement. Bon, j'ai donné mon consentement quand je suis venu tout à l'heure, un truc que j'ai pas compris, hein. J'ai dû cliquer sur un truc. Là, quand je me suis connecté.
Hein?
Quand je me suis connecté,
Oui?
il m'a demandé un truc, j'ai dû cliquer, je ne comprenais pas ce que ça voulait dire.
Tu peux essayer, tu peux commencer à essayer de partager tes
Oui,
slides.
alors, oui, j'étais un peu inquiet parce que j'ai pas de voix depuis ce matin, donc c'est pas le bon plan, ça. C'est bon?
Oui, oui, c'est parfait. T'as pas quoi?
J'ai pas de voix.
Ah oui, j'ai remarqué, je me dis, c'est bizarre, je ne reconnais plus la voix de Michel.
Bon, alors déjà, j'essaie de pas parler trop fort parce que ma femme est en réunion dans la chambre d'à côté et les
Ouais.
murs sont pas très larges. Et en général, je lui ai dit que je parle trop fort. Donc je me dis qu'avec le micro, ça doit passer. Tu m'entends bien là quand même?
Là, ça va, oui.
Ouais.
Ouais.
Ouais, j'ai investi dans le truc de cosmonaute là. Euh,
Bon, j'espère que de temps en temps, j'ai quelques coupures Internet. J'espère que là, ça ne va pas le faire.
pratiquement, le premier truc que j'ai fait quand il y a eu le premier confinement, c'est d'acheter un câble Ethernet et je l'ai branché directement à la box parce que sinon le Wi-Fi est compliqué.
D'accord.
Même en plein milieu, toi près de Paris, en ville et tout, c'est pas super fiable.
Bah, moi, j'ai une petite. Je ne sais même pas si ça marche avec le câble. Il n'y a rien. Il y a que le Wi-Fi, en fait. Là. C'est une petite.
Je-
C'est un petit routeur, je ne sais pas, Wi-Fi.
ouais, j'ai pas posé la question, ça m'a paru évident, c'est en anglais.
Oui, 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 tout à fait. Oui. D'ailleurs, là, il y avait un auditeur qui s'est barré parce qu'il nous a vu parler en français. Alors, je sais pas.
Ah,
Alors, comme c'est une collègue de la fac, je vais lui envoyer.
sous la si on m'oblige, je parle anglais, il n'y a pas de problème. C'est ma blague préférée, ça, c'était quelqu'un qui avait commencé un exposé, une réunion en disant Well, let us speak the most international language, bad English.
Et tu as toujours un contact avec Ahmed Elias?
Un petit peu, là, on a soumis un papier il n'y a pas très longtemps, non, il a été accepté, je ne sais plus. Donc pas plus que ça.
D'accord.
Je le vois sur Facebook de temps en temps. Je ne suis pas toujours d'accord avec ce qu'il poste, forcément.
Ah,
Là, il commence à mettre des trucs dans des journaux norvégiens, donc là, je ne sais plus. Et là, il a un poste en Norvège, tu sais, il est à Saint-Ef.
où ça?
À Saint-Ef, je pense que c'est à Oslo. Il a un poste
Ah,
d'ingénieur, donc là, je pense qu'il est parti pour rester, quoi. Enfin,
d'accord.
c'est un bon endroit, hein. Ils font des
Oui,
choses
je crois que
intéressantes.
j'avais entendu dire qu'il était parti là.
Mais il a d'abord été un postdoc avec Florine Radou, je crois. Et bon, là, ils sont plus forts que nous en publication. Je peux dire que ça va pas, il n'a pas perdu de temps. Là, nous, on a réussi à faire deux papiers pendant les 3 ans, un peu compliqué, mais là, ça a été bien. Et puis après, il a eu ce poste-là, ça fait un peu plus d'1 an, je pense déjà. Plus d'1 an, je ne me rends pas compte. Et donc là, on ne travaille plus vraiment ensemble.
Voilà, c'est fait.
Comment ça fonctionne d'habitude enfin, c'est compliqué de faire des questions au milieu. Tu veux que je m'arrête à un moment? Là,
Euh, non, les gens ne posent pas de questions au milieu. En général,
Ouais.
les gens posent des questions juste à la fin.
Si, ouais. Si tu veux faire un break là, à la fin de la partie 2, qui est en fait la plus grosse moitié, enfin, c'est un endroit, je peux m'arrêter un moment là si tu veux qu'il y ait des questions sur la première partie. Quoi.
Ok, oui, ben, oui, tu peux proposer ça, pas de problème.
Ça peut être un bon plan.
Ouais. Alors, nous, c'est les vacances en ce moment, donc peut-être qu'il
D'accord.
y aura moins de gens que d'habitude, mais
Ouais.
j'espère quand même qu'il y en aura assez. Il y a
Comme je
quelques
sais pas comment,
irréductibles, il y a quelques personnes qui sont tout le temps là. Après, c'est très variable.
comme je sais pas comment c'est d'habitude, c'est pas grave, je me rendrai pas compte.
Donc, je ne vais pas te dire.
Voilà, c'est ça. Écoute, je crois que le séminaire que j'ai fait où il y a eu plus de monde, c'est celui que j'ai fait à l'Énith. Hein. J'ai jamais une salle aussi pleine quand j'ai parlé.
C'est vrai?
Ah ouais, c'était impressionnant.
Alors, tu l'avais fait au séminaire du LAMSIN, donc c'est ça, hein?
Oui, c'est ça, oui.
D'accord. Ouais, si je me rappelle, oui, oui, je crois me rappeler parce qu'il y avait les collègues du, du labo d'hydraulique à côté.
Ouais.
Je crois que tu as fait un truc sur les milieux poreux, non?
Oui, oui, bah, c'est la même chose à peu près la même chose qu'aujourd'hui. On a un peu progressé depuis, mais on a rajouté la
D'accord,
posteriori, je pense.
d'accord. Et ça, évidemment, ça a intéressé aussi les collègues du labo d'à côté, qui est le labo
Ouais.
d'hydraulique. Et je pense, oui, ok. Non, mais c'est bien ce séminaire, quoi. Donc, il y a pas mal de gens qui viennent régulièrement, c'est bien. Bah, ici, on n'avait vraiment pas de séminaire et j'ai lancé ça cette année. Donc là, on arrive à avoir quasiment tous les 15 jours un séminaire. Alors, j'ai commencé par
Ouais, j'ai vu qu'il y a.
inviter les amis en attendant pour faire démarrer la
Ouais, enfin,
machine, quoi.
ça fait un bon programme. Tu as des bons amis, quoi.
Voilà, exactement.
Je
Et,
parle pas de moi forcément, mais
si, si.
ça fait un programme distingué. Je suis content
Euh,
d'en faire partie.
Et, et donc, non, mais ce qui est bien avec les amis, c'est que bon, voilà, tu peux les contacter direct, tu peux les harceler s'ils te disent non, discute.
Oh,
Tu
moi,
peux
je
pas
dis
te
jamais non.
permettre trop de le faire avec des gens que tu connais un peu,
Ouais.
très peu, quoi. Tu vois, ils te disent non, c'est
Oui,
non,
oui.
quoi.
Je dis jamais non.
Et c'est marrant parce que, alors, parmi mes amis, il y a des gens qui n'ont pas répondu. J'avais envoyé un mail groupé les gens de Poems
Ouais.
et j'ai eu très peu de retours. Alors, j'ai eu un de
Ouais.
Sophie entre-temps. Ben, je lui ai dit, qu'est-ce qui se passe? Pourquoi tu n'as pas répondu? Elle m'a dit, non, non, parce que je voulais pas qu'on te réponde tous en même temps. Ah bon?
Ah,
Et je lui ai dit, ben, j'ai eu que deux réponses.
ah oui.
Et donc, elle m'a dit, oui, oui, non, non, je le fais avec plaisir. Et je n'osais pas trop poser la question parce que je me dis peut-être qu'ils étaient gênés parce que c'est l'Arabie Saoudite ou quelque chose. Tu vois. On ne sait jamais.
Ah, on s'en rend moins compte à distance, on va dire.
Et voilà. Bon, ben, elle commence à avoir du monde là. Donc, on va
Ouais.
switcher en anglais pour ne
So
pas gêner.
switch to English. Okay.
Je ne crois pas que.
Let's pretend we can talk in English.
OK.
Fine. So what language you speak day to day here? Arabic or English?
And English. But some students ask us sometimes to make the translation in Arabic.
Oh.
But I don't
So
have
how different is it between the?
I don't have the technical terms in Arabic. I
Right.
tried
Yeah,
and
I know.
tried.
I understand. Sometimes it's even that in French. It's something I haven't never said in French or something. Yeah. Is it different language than in Tunisia? Is it very or can you just everybody understands you?
You know, it's a different dialect, but the root is the same. It's the classical Arabic, but in
Uh-huh.
each Arabic country we have some words that you know it depends from the influence. In Tunisia, we are influenced by the French period, Ottoman period, and we have
Uh-huh.
Amazigh
Yeah.
roots. Then you find some words in all these cultures, and here it's different. You can have other influences.
Right. Should I've switched to full screen. Is that better, or is it?
Yes, yes,
Does it make
probably.
it? Ça marche. Ok. You know, they can only see the top of your head, not your full face.
This is the biggest It's full
Yeah,
speed
they
then?
have to position the.
We will wait for more, perhaps 3 or 4 minutes.
No problem. Nobody ever starts on time.
Sorry?
Nobody ever starts on time.
Okay.
I've been told that in Germany they always start like 5 minutes late, but exactly 5 minutes late. So it's. And once I came late to a seminar at INRIA, and I complained because that started on time. Next week there is this big World Computational Mechanics Congress that was supposed to take place in Paris in last July, and they moved it completely online.
Okay.
So you had to record the talks, and the only thing that will be live are the plenary talks, but everything else is taped.
Okay.
There's going to be like
I'm going to record your talk too.
it's a short version of this one, so.
Okay.
But there's some nice stuff with this. The mini symposium looks good.
Okay. Okay, we start in 2 minutes. Welcome everybody. I will send the slides and the record of the talk and put the link on the website of the webinar. And for all students who need a certificate, you can just send an email to ask me to prepare it. This is my email. Okay, I think we can start. I I'm very happy to welcome Michel Kern for this webinar. Michel Kern is a senior scientist at Institut National de Recherche en Informatique Automatique, INRIA, a research institute in computer science and applied math in Paris, in France. And the research topics of Michel Kern are scientific computing, high performance computing, numerical methods for flow and transport in porous media, algorithm for coupled problems and directive transport, and decomposition methods on space-time domains. And the talk of uh, today is about how we should stop iteration and domain decomposition method. Okay, thank you, Michel, to accept our invitation, and we can start, I think, the conference today.
Thank you very much, Nabil. Thank you for inviting me to this seminar. Usually people say I'm very happy to be here today. Well, I'm very happy to be home today, but I'm very happy to be with you today and to be able to give this talk in the conditions that we know. You gave the title. I want to acknowledge first my co-authors. Sarah Ali Hassan was a PhD student, worked on this project. Elias Ahmed was a postdoc, and my two colleagues, Caroline Jaffe and Martin Voralik, who's actually my boss. And we also thank our funding agencies. So a summary of the talk is, the answer to this question is earlier than you think, but I hope you'll stay for the long answer. It's going to take a while. So I'm going to start with inflicting you with some physics of flow and in porous media, just the minimum so you can understand where the equation I'm solving comes from. Then I'll go to something much simpler, and I'll start with steady state linear diffusion problem where everything is reasonably easy to explain. Domain decomposition, and then I'll show how we can devise a posteriori error estimates and how they can help to decide when to stop the iterations. The trick will be to separate the error that comes from the discretization from the mesh and the error that comes from the iterations. Once I've done that, I'll show how you can generalize the ideas to the transient time-dependent case, first on a linear diffusion model, then a non-linear diffusion that looks like two-phase flow in porous media, and then how you use the ideas to, again, implement a posteriori error estimates. So we'll start with where this problem comes from. This slide is nice because it reads from right to left. We've worked a lot with the French National Agency for Radioactive Waste Management. France uses a lot nuclear energy for generating electricity. 75 to 80% of our electricity is nuclear. And you have to do something with the spent fuel, for instance. These are something called high-level waste, long life, 100,000 to millions of years, and pretty nasty. And the plan in France is to bury them deep underground, 500 meters deep, somewhere in the east of France. I can tell you where not to buy a house, and hope in a layer that is 100 meters thick and is very little water goes through, and hope devise things so that over a long period of time, radioactive decay plays its role, and almost no radioactivity goes into the surrounding water. So you can see here, do you see when I move my mouse? Is that useful? You can see here the canister that is about 1 meter high that contains the waste. This is a cartoon of the storage area that will be around here. That's a few kilometers across. And the geological picture here is a few tens of kilometers across. So this is a small area and 500 meters deep. So that's mostly a motivation. I'm not going to go into more details than that. There are several challenges. The simulation in subsurface flow, one of the challenges is that the medium is heterogeneous with material properties varying over several orders of magnitude. You also have different time scales from the years to 100,000 of years here, and also space scales, as you can see. And so one possible solution, by far not the only one, is using space-time domain decomposition methods. and using error estimates to decide when you can stop the domain decomposition iterations earlier than just fixing a threshold and iterating. So I want to say a few words about what's a porous medium. The subsurface is a porous medium. It's a medium that has pores. There is a rock matrix, and the fluid flows in the pores of the medium. They can be on several scales, as you can see here, thicker or thinner. And you don't want to, well, you could, but there are people working on the pore scale, but it's very hard to work on the pore scale for a geological scale medium. So what you want to do is some sort of upscaling. And the useful definition is the representative elementary volume. That is something that is large enough that you can average over it and small enough that you can still do meaningfully continuum mechanics. So we'll work over a VAR and we'll look at the geological scale. So we have things like pressure and velocity and things like that that are well defined. On the other hand, we look at two-phase flow when we have, let's say, oil and water or gas and water. Usually it's going to be, or in my talk, it's going to be mostly gas and water. At the microscopic scale, there is a sharp interface well defined where the phases separate. But if we look over a VER, then we have a macroscopic description, and we'll use a notion called saturation, which says what is the percentage of each of the fluids at a point, which of course doesn't make sense microscopically. It's sort of a volume of fluid, sorry. So the saturation is by definition between 0 and 1. And again, by definition, in the fluid, you have either water or gas, so they sum to 1. Then there's a phenomenon called capillary pressure that induces a difference between the pressures of the two phases. And phenomenological, whatever, you can approximate it by a given function, known function of the saturation of the gas, for instance, which is what I call pi in the following, or p if I forget how you pronounce in English. It's an increasing function. And there is a fundamental law in subsurface flow that is again an approximation, but has been put in rigorous footing by work by Grégoire Allaire, that is called Darcy's law, that says that the velocity of the fluid is proportional with this coefficient k to the gradient of the pressure, taking into account the gravity. K is a function of position that characterizes the rock, and this is the quantity that can vary over several orders of magnitude. It's analogous to a resistance. The smaller K, the less the water can flow through. The larger K, the more water can flow. And now in two-phase flow, you have to take into account that one fluid prevents the other from flowing. So you have to modify the Darcy's law and introduce something called the mobility that is again taken as a known function called here lambda of the phase saturation. On top of that, then now you can write conservation laws for here I've made several simplifying hypotheses, especially incompressibility, no gravity. So this is conservation of mass. We view the velocity of the fluid phase. So you write one of these equations for each phase, then Darcy's law for each phase again. And then you complete this equation by the fact that the closure relation, the saturation sum to 1, and you know the capillary pressure. So if you count everything, you have 4 equations with 4 unknowns, and there's lots of tricks you can play to simplify the problem. And I'm going to not only simplify it, but butcher it to make it much, much simpler. So I'm not much interested in this talk. That's a horrible simplification. On the pressure side, and I'll concentrate on the equation that defines the global mobility. In principle, they are coupled. So you see that the second term of the equation, the last equation here, involves the velocity, but that this time I'm going to ignore. And for reason I'm going to explain, I will just look at the first part of this equation, that is a standalone equation for saturation. Again, that's a very bad oversimplification. That's, well, not justified, but we want to look at the phenomenon called capillary trapping. one phase cannot enter some part of the medium, and you can see that phenomenon on the equation I'm going to look at. So, and it's been studied by several authors previously. So after, again, looking at the equation, making some transformation, I call U the gas saturation, doing mathematics, and you have two nonlinear functions, the capillary pressure P and the mobility. And you can show that you can end up with this nonlinear diffusion equation here for the Laplacian of phi of U, phi being a function related to both global mobility and capillary pressure. If my mouse, yeah, my mouse moves. On top of that, you have boundary conditions. And so this is valid as long as the functions that depend only on U, but not on the position. Now, there are several situations when you have what's called two rock types. A rock type is a part of the domain where we have one definition of the capillary pressure, for instance, and in another part of the domain, you have another definition of the capillary pressure. So actually, the function P here will depend on position. If you make the hypothesis that you have two domains like that, of course, this can be generalized to more complicated situation, then you can write an equation like that in each of the domains, plus some continuity conditions, expressing physical continuity of some of the quantities across the interface here. And I'm going to go into more detail on that because that's the fundamental part of the model here. So I'm keeping this equation. This equation is valid in each part of the domain, and now I have to specify how to transmit what information you transmit across the interface. So in the situation where you, so here is you have a picture of the two capillary pressure functions, and this is a situation where this hypothesis is not satisfied. But in the part where I can do that, I can draw a vertical line. My mouse doesn't want to move sometimes, it's pain. I can draw a horizontal line here. And for physical reasons, the phase pressures are continuous. So the capillary pressure should be continuous too. But if the capillary pressure is continuous here, then the saturation cannot be continuous. So you have to express the condition that P of U is continuous across the interface, but not U itself. And you have P1 of U1 on one side equal P2 of U2 on the other side. Except you cannot do that here or here because you have only one function defined. And the solution out of that is to truncate the capillary pressure functions. So you're not in the non-matching case. And then you work with the truncated functions that are still increasing, but not strictly increasing now. And there is a generalization of this work by Brenner and Kansas and Hillhorst, where they don't truncate in that direction, but they use graphs. And that's a more demanding mathematically, but a better generalization. So we'll work with the truncated function, and the condition we have is P1 bar of U1 equals P2 bar of U2. And the second condition is to express the continuity of the flow across the flux across the interface, which involves yet another function phi. So you have two nonlinearities here, P and phi. And it turns out that phi of U is not continuous across the interface. So you have to be careful with the regularity of the solution here. So having said what problem I want to look at eventually, I'm going to go to something much simpler. First, I make the diffusion linear, and then I'll forget about time. So for the beginning of the talk, I'll look to what's called Darcy's equation, or the linear diffusion equation. I've written it here in mixed form. So introducing the R the flux again, U is the pressure, D is the permeability, notation changing every time. And if you look at the overall domain, then you have some boundary conditions. Now to mimic what we've been doing with the transmission condition, we'll look at the case when you have two different subdomains, but in this much simplified setting, U is continuous. There is no capillary pressure, so U is continuous across the interface here, and the fluxes are continuous. And you can start doing using domain decomposition methods with these conditions, but we want to do something slightly different. we are going to use equivalent transmission condition by taking linear combinations of the natural ones, U1 equals U2 and R1 equals R2 U2, multiplied by this bit number beta. I'll say what they are in a second. And you end up with what's called Robin transmission conditions that are strictly equivalent to the previous ones, but are more flexible to work with, let's say. You can get better convergence. This all goes back to work by Pierre Williams, which I'll quote in a second. And so having said that, these two problems are equivalent. And now I'm going to define an iterative algorithm, a domain decomposition algorithm for solving the problem, working on over each subdomain. So at each iteration, K will always denote the domain decomposition iteration. So at each step K, I'll solve two subdomain problems. So during all of the talk, I'll restrict to two subdomains. Of course, everything can be generalized to more than two subdomains. So you solve the same problem over each subdomain, and now you have to incorporate the transmission conditions, and they are going to be used as actually boundary conditions. So for instance, on subdomain 1, you solve for these equations with boundary condition on this part of the domain, and on the interface, which is now a boundary for subdomain 1, I'll have a Robin boundary condition with data coming from the other subdomain at the previous iteration. So this is known. K minus 1 is known. I'm computing K now, and same thing over the other subdomain. So this is easy. It's easy to see that this is a well-posed problem for each K. And it's not as easy to see, but that's work going back to similar work by Pierre Williams. You can show that this algorithm is convergent using energy estimates. And it's now a well-known game to find out what the best beta parameters are. You can do that by doing some Fourier analysis, assuming the interface is straight and infinite, compute actually a convergence rate and optimize the convergence rate. There's a lot of work by Caroline Jaffe and colleagues, and Martin Gander has a whole industry over this kind of methods. Very nice work. So this is the algorithm we are using for domain decomposition in the steady state case. Everything works fine, convergent method, fine. At the discrete level, because it's important to conserve mass in this the application we're looking at, we are going to use mixed finite elements. So for those of you who are not familiar with mixed finite elements, you approximate at the same time both the pressure, the U function and the R function. U is a scalar, and it's going to be approximated by a function that is piecewise constant on each element. So let's say at the center of the element, the pressure here. And the velocity or the fluxes are going to be approximated by a vector field. And it's enough to know the normal flux through each of the edges or faces in 3D. These are the so-called Raviart-Thomas mixed finite elements. And you have also other families of finite elements following Bredzi and colleagues. And for future reference, we'll be using broken Sobolev spaces, that is functions that are locally regular, but not globally, because they are piecewise constant here. And also for the vector fields. So the three norm is the energy norm, semi-norm actually, and the star norm is for vectors. So now I assume that I can solve the domain decomposition problem. It's convergent. I've got a solution. And now we can start addressing the question, when do we stop the iterations? So to do that, Martin Voralik basically suggested that you can use a well-defined a posteriori error estimates. And so the goal here will be to bound the error between the unknown solution and not quite the computed solution, but the post-process version of the computed solution. I'll say what it is in a second. So this is unknown because you don't know U. And you want to bound that without any unknown constants here. So completely explicitly by computable, fully computable estimators. And on top of that, you want to distinguish the part coming from the discretization with the part coming from the domain decomposition. So some references. This goes back to work for Prager and Singh, and then the people near Paris in Cachan have worked a lot on that, and Martin Voralik has revived the whole thing. That was all in the beginning only for discretization error. It's been extended to taking into account error from algebraic solvers. And in this talk, we also extend work by people from LMT, yes, École Normale Supérieure in Saclay, Valentine Ray, Christian Ray, and Pierre Gosselet, who did that for Neumann method and Feti. And their work assumes that at least one of the fields is either H1 conforming or HGIF conforming. And here, because we're using Robin transmission condition and mixed finite elements, none of the fields we compute are continuous, so you have to regularize everything. And so we want to develop a posteriori estimators for DD algorithms where neither the flux nor the potential, that is the pressure, are conforming. So here again, we'll want to have fully computable estimators depend on reconstruction of an HD flux and an H1 potential. And the first problem is that your solution, UHK, that is the solution computed by the mixed finite element method, cannot be used because it's piecewise constant. So its gradient is locally 0, and there is no way you can use the energy of the error as an estimator because it does not depend on the computed solution. So the first thing is you have to post-process that, and that's a classical, that's well-known trick. But then even if you do that, the post-process is locally regular, but it's not H1 conforming even at the subdomain level. It jumps between elements. And then because we're using Robin again, the fluxes are not HGIF conforming, and the solution itself jumps across the interfaces. So you have two levels of continuity. You have the on each subdomain having conforming H1 conforming on each subdomain, and then you have solutions that are H1 conforming, or fields that are H1 conforming across the subdomain. I'll try to be careful and distinguish that. That's important. So most the Martin Vorlik's work is based on reconstructing well-defined fields, either H1 conforming or HGIF conforming. So here we'll have three. One that is H1 conforming at the level of the subdomain, but not across the subdomain interface. That's a new one. Then we'll build one that is H1 conforming globally. That's the most classical one. And then we'll build a vector field that is HDIF conforming. That is the flux, the normal fluxes are conforming globally across the elements and across the interface. That's the technical part of the work. The ideas are here, and the next few slides are going to be much more technical. So the main result here is that we obtain the bound of this form, pretty nasty. The error between the solution and the post-processed computed solution, so again, this is unknown, is bounded by the sum of 4 terms, and we group them 2 by 2. The first 2 terms are related to the discretization. That's called the data oscillation that comes up in all of the estimators. It involves the source and how well the reconstructed vector field approximates the source. And then you have one that compares the post-process solution with one of the reconstructed solution that captures the scheme non-conformity. And then the next 2 estimators will compare the H1 conforming locally with the H1 conforming globally solution and the jumps of the computed flux with the reconstructed flux. And these 2 capture the DD potential non-conformity. So what I wish to emphasize is that there are no hidden constants here. This one is related to Poincare inequality. So everything here is completely computable. So this is a guaranteed upper bound. Those of you who may be familiar with this kind of work will note that we have no lower bound, saying that the upper bound is actually up to a constant efficient. I'll show numerical results that say that the method is efficient, but we have no proof of that. So this could be a very large overestimate. It turns out not to be the case, but we have no proof. So now all that's coming is showing how we compute all of these 3 quantities, the 2 potential reconstruction and the flux reconstruction. should be okay. And of course, at convergence of the DD method, the DD estimator will go to 0 and will be back to the case where there is only discretization error. So before jumping into the details, I want to try and picture the different fields. So this is the solution that's computed from the mixed finite element methods, the U. So as you can see, it's constant over each element and it's completely discontinuous. Then the post-processing will give something that is nicer locally, but still jumps across the elements. The next step will be to compute a solution that is continuous over each subdomain, but jumps across the subdomain. And this will help give an indication of the discretization error. This is an estimate of the discretization error. And the last one is the one that is fully continuous even across the subdomain interface. And this one will give an estimate of the domain decomposition error, and hopefully, well, will go to 0 when the DD iteration converge. So there are several steps. The first one is the post-processing of what should be U here into something that's called U tilde, and that goes back to the paper by Arnold and Brezzi and Arbogast. You want to compute a solution. So you have a U that is, you have both a locally constant scalar function and an HDiv conforming flux over each element. And you want to compute something that is a second order polynomial locally that has the same average as your computed solution and that also has the same fluxes. And this is a very simple local computation, no system of equation to solve. So I won't spend a lot of time on that. Then you begin by reconstructing the fully conforming solution even across the subdomain interface, because that's the one that most looks like what's done without domain decomposition. And this is very simple again, because it's just averaging. So for each vertex, you take the average over all elements containing this vertex, and that gives you, by construction, an H1 conforming solution. If you're into parallel computing, you'll note that if you're doing parallel computing, then this will involve communication across the subdomains. There is no avoiding that I know of. So that's more or less what's been done in previous work. And now we want to construct a solution that is conforming H1 locally over each subdomain, but not across the subdomain, but will still be more and more continuous as the iteration progress. So you want it to be locally H1, and the first thing you do is over each subdomain, so each of the squares here, you take all the interior nodes and you do the same thing as previously. That is, you do the averaging. Now you have to do something different for all the vertices that are on the interface. And to do that, you're going to do a weighted average of different solutions. And the weights are going to be updated during the iterations. So they depend on K here. At the beginning, the weights are only local to one subdomain. So that's one subdomain. As the iteration progress and tend to convergence, then they look more and more like the weights you have in the overall averaging. And so that's how you can build this second field that starts completely local and ends up looking more and more like the conforming one. And so it will carry the DD error. And now the worst one is the flux, the vector field flux here. Since the computed one is not globally HDiv until you have convergence, you want to build something that is globally in HDiv, that is the fluxes match, the normal fluxes match across the subdomain interface, and also that is locally balanced with the source. So that's over each element on the average. And the first idea is to use the jumps of the fluxes across the interface, but you cannot do it. That would give you by construction an HDiv conforming flux, but you still cannot do that because you would lose the mass balance in the triangles that share an edge with the interface. So that's the first idea, but you have to do something else. You have to modify that idea to get what you want for the second criterion here. And the thing is to solve a small coarse problem by adding corrections here to restore the mass balance over the interfaces. So this is the problem we are going to solve, adding these corrections for each. You have one equation like that for each subdomain, but you have actually more unknowns. You have more interfaces than subdomains, and you also have to take into account the boundaries. So you have to solve that in the least square sense. That's in some sense analogous to the balancing step you have in some domain decomposition methods. But that's somewhat ad hoc, and we're trying to work on a better solution than that. So in any case, it's going to be a small linear system, least squares linear system that gives you corrections that are local over each interface. But if you do that, you've restored mass balance across the interface, but you've lost mass balance in the elements that share an edge with the interface. So you have to work with small bands across the interfaces in colors here, and again correct once more to restore the mass balance that you've lost in these elements. So that's the last step. Once you've done that, you have everything you need. And the theorem, you apply the theorem in the few slides back with these quantities, and it tells you that you get, if you compute everything that's on the right-hand side in the sum, then you get all these indicators, and you know that it's a upper bound for the solution. So how does this work? Well, if I'm giving a talk that it works well. To try and illustrate, we are working with the known solution here, so we can actually compute, of course, what's supposed to be computable, that is the estimates, but in that particular case, we can also compute the error so we can compare. That's, of course, an academic problem. So on this picture, you have the total error in black here and the estimator in red. And as you'd expect, because the theorem says it should be, the estimator is larger than the error. How much larger? When a little bit, at the beginning somewhat, and so here is the number of iterations, and here is the size of the error and the estimator, and this picture shows the ratio between the two. So it starts at 7 and it ends up close to 1, which is the best you can do. So the method appears to be fairly efficient. Again, we have no proof of that. And the last picture here shows the different parts of the estimator. Actually, so we don't have the different parts of the error, but we have the parts of the estimator. And since we know the estimator is not much bigger than the error, that makes sense. So that's again the total estimator, and then you have the estimator that estimates the discretization error. Does not depend on the DD iteration. Makes sense. The mesh is always the same. And then here you have the estimator of the error that's due to the domain decomposition. And as expected, this one goes to 0. And what you would have done in a standard iterative method is say, well, I'm going to iterate until the residual is divided by something like 10 to the minus 6, 10 to the minus 8, or whatever. But actually, the idea is that you can stop here when the error is just some factor below the discretization error that is always going to be here. This is wasted work in some sense. So you can stop much earlier once you know that you've gone below some threshold times the discretization error. So you can stop the iteration in that case after 6 instead of 40. At least you can decide when to stop the iterations without wasting work. And these pictures show the actual spatial distribution of the error. So that's the actual energy error, the total estimator here, which similar but larger, a little bit larger. And then you can distinguish between the discretization estimator, that is where the solution is, but and the DD error that is concentrated on the interfaces, not very surprisingly. So I think that's it for the first part, that is a linear steady state diffusion. And maybe if you want, I can stop and take questions now for this part, or I can move to the second part. Everybody's dead, so I guess I could carry on. So now I want to extend these ideas to the transient case, first linear diffusion and then nonlinear, and then a posterior error estimates. So if you want to do domain decomposition for a time-dependent problem, there is at least two ways you can do that. There is the standard way, and then there is our way. And most people, and it works fairly well, have done something that at each time step, you solve a steady state problem, and you do that with domain decomposition. And once you've solved the problem at this time step, then you go to the next time, you exchange data across the interface at each DD iteration, it converges, you move to the next time step, you do that again. That works fairly well. The main drawback that we can see is that it forces you, or it's very hard not to have the same time step, thank you, over the whole domain. If you want to do local time stepping, one solution is to do space-time domain decomposition, where now I'm going to switch the iteration and the time stepping. That is for each, for each domain decomposition iteration, I'm going to solve a full space-time problem over what's called a time window, the whole time interface here. Then move to the next iteration. And at the end of the DD iteration, I'm going to exchange values over a space-time interface now. So the quantity of information that is exchanged is the same. You just don't do it at the same time. And this would be somewhat better for parallel computing because you exchange less often and more data at the same time. But that's a detail. So this has been studied by people around Laurence Alpern and again, Frédéric Nataf, Martin Gander, or in a different context by Xavier Antoine for Schrödinger's equation. And Caroline Jaffe also, and we've shown that we can use different time steps in the different subdomain depending on the physics. It might be useful to be able to do that. There's a whole lot of work by colleagues of Caroline Jaffe and Laurence Alpern on this kind of ideas. And we've shown how this can be done with mixed finite element methods in Feng Hong's thesis. So this is the method we're going to study for the rest of the talk. So now, before going into the full nonlinear problem, I'm going to look at the time-dependent linear diffusion equation. So if you want, phi of u before is d du. And again, I'm split the domain in two parts. I write the equation in mixed form for a time-dependent problem. That's not as standard, but it's becoming to be well known now. Again, two subdomains, so I have to have transmission conditions. And the transmission conditions start as being the continuity of the pressure and the continuity of the fluxes. And as we've done before, we replace that by Rabin transmission conditions. And it's still equivalent, algebraically equivalent to the original problem, obviously. So from that, we devise an iterative algorithm that in that particular case is called the optimized Schwarz waveform relaxation problem. So you solve over each subdomain with boundary condition over this subdomain, Rabin boundary condition over this subdomain with data coming from the previous iterations. And to be very confusing, I've switched from number of iterations from k-1 going to k, from k going to k+1. I'm sorry about that. And again, you can optimize the parameters to get better convergence. And we've proved in this paper that this method converges for in this context for mixed finite elements. So you can prove rate of convergence and everything. It's also nice. I'm not going to spend a lot of time on that, to frame everything as an interface problem. That's a two-field, I think it's called two-field method. It's different from the sure complement method for a steady state problem like Neumann, in that you have to have one unknown on each side of the interface. So you take the boundary condition, your boundary data here. So this guy basically becomes your xi here. And given this xi, you compute that quantity that goes on the next subdomain. And so you call S the operator that, given the source and the initial data, takes xi and gives you back this guy. So it's a robin to robin operator. And you can show that solving the multi-domain problem is equivalent to solving this linear problem for over the boundary unknowns. If you solve this problem, it's a fixed point problem. If you solve this problem with a block Jacobi method, then you get back the previous algorithm. But now the interesting remark is that once you know that it's a linear equation, then you can use better methods than simple Jacobi. You can use GMRes, and that actually improves the convergence of the algorithm quite a lot. The matrix vector product, so to speak, or the operator vector to be applied is just solving one problem per subdomain at each iteration. And we've done that, and by combining that with optimization, you can get a very efficient method that converges quite fast for various conditions. That was part of Fung Hong thesis. Now I'm finally going to the nonlinear problem, but the idea is exactly the same. You have your local problem on each subdomain. So TTU minus Laplacian of phi of u, phi being your local function over each subdomain. And then you have your transmission conditions that are no longer the continuity of u itself, but of p of u and of the flux. And I probably should accelerate a little bit. And if you do that, then you can also play the same game as before. That is replacing these transmission condition by ones that are of a Robin type with coefficients that are no longer called beta, but are now called alpha. Sorry about that again. And there is a theory that this problem is well posed with fairly weak regularity. And we now look at an iterative algorithm, the optimized Schwarz waveform relaxation in that context. So you can have to solve this nonlinear problem over each subdomain with this fairly weird boundary condition. It's a Robin boundary condition with nonlinear functions here. So this is not obvious that it's well posed. We proved that by basically copying the proof for the Dirichlet boundary condition. You have to be a bit careful, and it's you start with a finite volume scheme and use compactness argument. That goes back to work by Emar and people like that. Paper by Alt and Lucaros. That's now Arkansas, and that's been done several times. So you have an iterative algorithm that can we haven't proven convergence. We have proved that it's well posed, that you can iterate the algorithm again. I'll say a few words about the discretization. We are doing this, in that case, we are doing a simple finite volume, 2-point finite volume approximation, where phi of u is constant over each u and phi of u are constant over each element, and we have to add unknowns over the interface here. So you discretize the equation in the interior with the boundary terms, and you also discretize the boundary condition, the transmission condition. So you have to add boundary unknowns to the equations. And for the computation, we've used a very nice MATLAB toolbox written by a group of, around Knut Andreas Lie in Norway, that in particular computes, has automatic differentiation. So you just write these equations and it will give you the Jacobian matrix for free. That's fairly nice from an implementation point of view. So all of the results I'm going to show now have been obtained with this toolbox. And the last ingredient is the time discretization. We use discontinuous Galerkin in time. That's almost a fancy way of calling backward Euler, but you have to be careful on how you compute the right-hand side. That's the main difference. Otherwise, it's the same as backward Euler. And the feature now is if you have different time steps over the different subdomains, because you don't need to synchronize at each time step, each subdomain will evolve in its own way. At the end, you have to exchange the information, and you can do that by using time projection, L2 time projections, using algorithms devised in those two papers that can let you use completely different time steps. All you have to do is figure out how the intervals overlap here. but that can be done in a very efficient way. So that's the main strength of this method, is that you don't need to have, you can have different time steps in the subdomains. And also just one example, when you inject, I never remember whether it's gas or water, so the solution, you can see, moves across the interface that is not straight in that case. And here we compare the case when you have conforming fine mesh in blue here, no, in red. So the error is negative here. So the higher up you are, the better. So that's the error with 3 different time grids. So the mesh, the space mesh, is always conforming in my talk. It's just the time grid that can change. So in red, you have a fully conforming fine mesh. In green, you have a fully conforming coarse mesh. And in blue, you have a mesh that is fine on one side and coarse on the other side. And what you can see is that it works almost as well as the everywhere fine mesh for hopefully a somewhat cheaper implementation. And this is a nonlinear example where you see it's called capillary trapping. So water, gas is injected from this side, and you can see that it enters this low capillary length here, and that it actually does not, well, very small, very little of it comes out. So that's a fully nonlinear feature. You could not have that in a linear diffusion problem where the solution would be non-zero everywhere. And that's just showing the convergence of different optimization procedure with the iterations. So this was without any a posteriori estimates. In the last part of the talk, yeah, 5 minutes should be good. I'm going to show how to extend these ideas to this new setting. So what's going to happen is that you have to add an estimate that's related to the time discretization. So what changes? Well, you have to take into account the time dependence. That's basically done by comparing piecewise constant and piecewise linear approximation, but that's free. And that's explained in details in Ali Hassan's thesis and in that paper. That's also, it works in the linear case. In the nonlinear case, there is a tricky question, which is, do you work with U or with phi of U? And it turns out that it's better to work with phi of U. And if you need it, but you actually don't need it in practice, to reconstruct U from phi of U. And then you have to take into account the non-conforming time domain decomposition. So we are using a somewhat simpler procedure with just 2 fields, one scalar and one vector field here. The procedure for computing the Q part is the same as the sigma before. You approximate the fluxes by this quantity. So basically finite volumes and mixed finite elements are very closely related. You can get Rierthoma conforming fluxes from the output of the finite volume computation. Then you solve local problems to get to post-process phi, and you post-process the saturation if you need to, but that's only for the theory. You don't actually do it. And then you compute the reconstruction by averaging, and you have to modify, because the solution itself is not continuous, but P of S is continuous, then you have to modify your reconstructed solution across the interface, and then to make sure that you still satisfy the mass balance here by using a bubble function that will not change the values across the interface. And again, you work with S and not with phi, well, with phi of S and not in with S. And so the estimate that you get is something that takes into account the space discretization, compute these 2 quantities. This one is the same as before. The second part takes into account the time discretization by comparing linear in time and constant in time solution. And then the DDR will be coming from the comparison of the fluxes, the computed one and the reconstructed one. And you can also, but I haven't shown that, include Newton linearization, because you're solving a linear problem at each time step. You can include that as shown in that paper by Martin Woralik. And so I'm not going to give the details here, but pretty horrendous. You defined distances, two notions of distances, because the solutions are have fairly weak regularities. The only thing that is in H1 is this guy, not U itself. So this, I'm not giving the details here. If you do that, you can obtain an error bound by one of the weak distance can be bounded by something that involves the initial condition plus the 3 estimators I showed before. This involves the time, but it's supposedly very small. The initial condition, you can control it. And then the strong distance under this technical assumption here, you can also bound the strong distance by the same estimator. So that tells you that, again, you have something, you can bound some error measure. The trick is to defining the proper error measure here by things that are fully computable here. The proof is more or less the same as this paper. The catch is that I've lied to you. This technical assumption is actually not a technical assumption, it's cheating, sorry. It means that this second part of the result is only true. Basically, for that condition to be true, it means that the capillary pressure must be continuous. Except I've told you at the beginning that I wanted the capillary pressure to be discontinuous. So in the interesting case, we don't really have a result yet. I'm not sure we can have one, but the method seems to work. It's just not justified theoretically for the moment. And so to basically stop, I'll only comment this one. Shows again comparison of the various estimators. So the total estimator is in black here. The space-dependent part is in blue, and the time-dependent part is in green here. And the red one is the part that depends on the DD iteration. It's basically the only one that depends on the iteration, except the time one at the beginning. And so again, instead of stopping when the residual is at some fixed threshold, you can stop when the residual gets below the smallest of the estimators related to the discretization here. And if you look at where the error is, well, the global error is with the solution, but the DD error is with at the interface of the subdomain. And the same is true if you advance in time. The global error follows the solution. The DD error remains on the interface. Not very surprising though. And another example where the subdomain boundary is aligned with the flow, the method still works and the conclusions are more or less the same. You can stop much earlier than what you would have done by iterating to a fixed threshold. And that's again a comparison of the errors with the solution and with the interface for the DD estimator. And with that, I'll conclude and I'll leave you with some references, and thank you for your attention. I'll be happy to try and answer questions. Sorry if I had to run through the last part of the talk. Nabil, are you still here?
I'm sorry, Michel. My microphone was.
Yes, I know.
Okay, thank you. Then
sorry,
thank you for,
sorry for waking you up.
Sorry?
Sorry for waking you up.
I was talking to you. I said that I'm sorry for your voice. Is there some questions? I see that in the attendance there is some colleagues that works on.
Bonsoir Michel, c'est Najla.
Bonjour.
Ça va, tu vas bien?
Ça va et toi? Well,
Najla, do you have a question?
It's been a long time.
Non, pour le moment, j'ai pas de questions. Bah, la méthode de décomposition de mail, je travaille là-dessus un peu sur ces problèmes-là.
Najla.
Speak in English.
For our friends who are English speaking.
Najla was a part-time PhD student in our group a long time ago.
Yes, I know. I know
It's
that.
good to hear from you.
And these estimates, then all the domain decomposition methods that you use here are without overlapping. Do you develop similar things for domain decomposition with overlapping, or is it
No,
more difficult?
I've never done overlapping domain decomposition. I don't see why it would not work, though you have to be careful not to count things twice in the overlap. The idea of the reconstruction should work the same, but I have absolutely no experience with overlapping methods.
Okay, but the difficulty is that these problems are not steady state, or is just for evaluating the estimation, the a posteriori estimates.
Well, they work in both cases. They work for the steady state, but they also work for the time-dependent case. That's what I did in the second part. There is lots of details in Sarah Hassan's thesis and in the paper by Ali Hassan, Jaffe Voralik in ETNA. The time-dependent case, it's quite involved if you do it with I mean, if you want to have sharp estimates, I think it gets quite involved. You have to have a lot of different reconstructions.
Okay.
So that's the part of the work with which I'm least familiar. In the nonlinear case, we simplified things to have not as many estimators at the risk of having not as sharp an estimate.
Okay. Okay.
So you should look at the ETNA paper if you're interested in the time-dependent case.
Okay, thank you. Is there other questions in the attendance? Fathi, you are
Just
here?
thank you, Michel, for a nice lecture for everyone. I'm reminded of perhaps some degenerate cases of some of what you presented. I'm reminded of a reference by Olenek and Radkevic, where there is a lot of theory to perhaps that can be used numerically for solving such cases where the operators degenerate on pieces of the boundary. I'm just adding this as a footnote, not necessarily. You have accomplished a very nice lecture and a very nice presentation. Thank you very much.
Probably not aware of that reference, so if you can get it to me through Nabil,
I'll be
maybe,
happy to,
I'd be interested. Yes, thank you.
Of course, I'll be happy to send you by. If I get from Nabil your email address, I will be happy to send it.
Okay,
immediately.
fine. Thanks.
Sure. Thanks. Thank you. I sent my email in the chat.
Okay, well, I'm sharing my screen and I don't touch anything, so I don't look at the chat.
Well, no problem. This is, I'm just saying hello to you and everyone here. Okay, so. It's thanks.
Rida, you work on domain decomposition method too, no? Rida Mdima.
Non, j'ai pas travaillé sur le domaine de composition.
Okay. Okay, thank you very much, Michel.
My pleasure.
There is no more questions. We will stop here the webinar, and I iterate my thanks to you. Thank you very much.
Thank you very much.
Okay.
The screen.
I will put the record of the talk and the slides on the website of the webinar. Merci Michel et à bientôt.
Merci. Oh, il y a plein de...
Thanks Nabil. Thanks everyone.
Michel.
Ah ouais.
Ouais, je suis là.
C'est bon, là, on a eu un bon nombre de participants aujourd'hui.
Je vois qu'il y a 25 là à peu près.
Non, on était à 34.
Il y avait plus avant.
34.
Il y avait plus avant. Bon, super.
Oui.
34 au moins.
Ok, merci beaucoup. À bientôt.
Merci Nabil. À bientôt.
Salam Nabil, salam Michel. À toutes.
Au revoir.
Au revoir.